All right, guys, let's dive into bolted connection design. So bolts replaced rivets long time ago. At first, they were viewed skeptically because rivets are extremely strong and robust, and they have a high clamping force. So at first, people were slow to pick up bolts, but over time, obviously now they're the way we do a lot of things. They're great for filled connections because they don't require welding, which tends to be sensitive, far more sensitive to environmental factors. So here's just a few types of connections. These are shear connections. Here's an extended tab. Here's a shear tab, so there's a plate on the back side. And here's a clip angle. Clip angles tend to be more common in industrial settings, and the shear tabs more common in commercial settings. Here's a few renderings. Um, Haunch, I'll just kind of flow through these since it's pretty much a visual thing. Moment connections. You can see here these heavy welds. Here's the joint prep. So that whole face where it meets a column or a flange is welded. Here's a heavy moment connection using plates on the sides. Another moment connection in the shop. You can see how much weld goes into these. These are runoff tabs. So this gets cut off and ground. That way there's room for kind of the crap of the weld to land here, and by the time they cut it back to here, it's nice and clean. Okay, some brace frame connections. This has been welded on. Here's a bolted version. These are unbonded braces. They're kind of came into favor 10 or 15 years ago. Heavy truss connection. So this truss was large enough it couldn't be shop welded. So where the members come together, they're just filled bolted with gusset plates. Some base plate connections. This one has oversized holes, which allows for some misplacement of the anchor rods, and then heavy washers go on top of those holes. Sometimes they're welded, sometimes they're not. Just depends. Here's an old base plate. Here's a base plate with a shear lug. So that lug goes down into the concrete, into a block out, and it's super effective for transferring large forces. Okay, so structural bolts, there's three main classes: snug tight, which are basically tightened with a wrench. Pre-tensioned bolts are tightened all the way, well, close to the bolt's breaking strength. And then slip critical are pre-tensioned bolts, but the surface prep is considered carefully. Different grades. AISC recently introduced groups, so group A, B, and C. C is fairly new. Group B is the old A490. Group A, which we use extensively, is A325. Keep in mind that there's a trade-off between ductility and strength. So the higher a bolt gets in strength, the less ductile it becomes. So if Group A bolts work for you, I would suggest going with them. If they don't, you need some extra strength. 490s. I've never seen Group C specified, but there's no reason you can't use them if the code permits them. All right, there's tends to be markings on the bolt which tell you, what grade it is. If you go to a job site and you can't see any markings, and sometimes they're not numbers, sometimes they're little lines, you need to ask more questions to find out if they use the right bolts. Nuts, we use heavy hex nuts, which tend to be larger than the normal stuff you buy at Home Depot. All right, different washer requirements. Unhardened washers you can use with standard holes. You also don't need washers if the bolts are kind of milled properly. Hardened washers we use on the turning surface at slip critical connections. That way there's no galling between the nut and the base metal. Galling is when like little balls or little gouges form, and that increases the friction, which decreases the pretension. If we have long slotted holes, we add plate washers to cover the hole, and then channels and S's. You can see here on this channel the flange is tapered, so it has a washer that's also tapered. And that allows this face and the top face that you can't see to be parallel. And then tension indicators, there's two types. One are these direct tension indicators. So when the bolt gets pre-tensioned, these little nubs compress, and using like a spark plug gap or those thin strips of metal, an inspector can slide them under, and based on the manufacturer's data that they provide, they can tell if it's tensioned up properly. And then these washers here have little paint pockets that when it gets to the right tension, those paint bubbles pop and squirt out. All right, low strength bolts we can use for low strength applications. They'll have an A307. Sometimes there's like little lines, different markings. If you don't have a number, then figure out what those little lines mean, and that's sometimes easy enough just with Google. All right, projection. Some people will ask, how far does the tip of the bolt have to stick out past the nut? Short answer is it does not. Well, the long answer is that as well. Basically, if the nut and bolt are flush, the nut has the strength to break the bolt. That's the concept. Here's some tightening marks. So in this case, it's agreed upon beforehand between the installers and the inspectors how the nuts will get marked once they're tightened. All right, you can watch that bolt video. It's not the most exciting thing, but it'll give you a feel for what's going on. All right, so some requirements on detailing, and this is important to understand how it's going to be drawn and built because that's going to flow into your calculations. So there's detailing requirements for all of these things, so let's go ahead and jump into them. First, the nominal hole size for bolts. It tends to be a 1/16 over the diameter. So if I have a 1-inch bolt, I have a 1 16 inch hole. There are oversized holes, so those are slightly bigger, and then short slots and long slots. We use oversized holes and slots when we think the mating parts aren't going to line up exactly. So if I'm connecting a beam to a concrete wall, I will use long slots because that buys me some tolerance if that wall is not perfectly plumb, or perfectly where it belongs, which happens. Concrete tolerances are at least plus or minus an inch. All right, so nominal hole dimensions. Here's a little bit of a discussion of when to use them. So for bearing connections, you can't use oversized holes because they allow for too much slip. So you can use standard holes or short slots where the force is perpendicular to the short dimension of the slot. And then slip critical, you can use oversized holes, long slots, short slots, because the force transfer happens through friction in a slip critical connection. So if the holes are bigger than the bolt diameter by a lot, then the friction carries the force. Minimum edge distances. So this table is a little outdated. It's actually this side now, where for a 3/4 inch bolt, which is the most common bolt, the edge distance is 1 inch. They got rid of these in one of the code versions recently. All right. Hole spacing. So the minimum is 2 2/3 times the diameter. Preferred is 3 times the diameter. But in practice, if you can use a 3-inch hole spacing, that's ideal because that matches shop equipment. Back in the day when dinosaurs roamed, the drill lines had drill chucks every 3 inches, so you could have multiple drill bits running at the same time drilling holes. And because they were 3 inches apart, that kind of became the standard spacing for holes. So usually for 1 inch bolts and under, we'll use a 3 inch bolt spacing. And then when you get to the larger bolts, then it needs to go up. All right, maximum spacing, you can read that. Basically, if we have a large lap joint where two plates or whatever are going across, we want to make sure there's bolts close enough to keep everything stable and tight. Anchor rod sizes. Let's say we have an 1.25 inch anchor rod. You can go up to a 2 16 diameter hole. And again, like we talked earlier, that is for the purpose as if the anchor rods on site were misplaced or slightly off. This gives the ability to not have to mess around with the bolts or the holes in the field. You can just set the column, adjust it, and then we put a washer, and it tells you the minimum size over the top of that hole to make up for the gap. I would suggest doing this on every project because when you stop and think about locating anchor rods, first surveying them correctly into position and not having them move during placement of concrete, things do shift, things are going to be off. So giving the field flexibility that they don't have to call you or stop the job to figure out what to do because an anchor rod is a 1/2 inch out of place. Okay, let's get into force transfer of bolts. If we have bearing connections, let's say the force comes from here, it's going to bear on the bolt head or the bolt shaft. It'll transfer through the bolt in shear and then back into the other piece of material in bearing and then back out. So that is a very common type of load transfer in buildings. The second is slip critical, where the bolt is pre-tensioned. That creates a clamping force between the layers, and that clamping force creates friction between the layers, and that's what transfers the force. So this force comes through, it gets transferred in friction here into this plate and through here. All right, different failure modes. You can check this out. So let's dive into strength. For tensile and shear rupture, which are the two primary failure modes for bolts, Phi is 0.75 for both. The nominal strength is the nominal stress times the area of the bolt. And this Fn, looks like that should be an Fn there. Okay, so Fn is either for tension or for shear based on this table. The area of the bolt is the unthreaded body area of the bolt, and you'll see why in just a second. So if we come to this table for Group A bolts, and the nominal tensile strength will be 90 kibs per square inch. The nominal shear strength will depend on whether the threads are excluded or included from the shearing plane. So if they're not excluded is how they terminize it, we're 54 KSI. If they are excluded, it's 68. I tend to always use the not excluded because I don't have great confidence, or full confidence is the better word, that that won't happen in the field. Bolt lengths get swapped based on need, and I think it's not quite accurate to think that if I say I don't want any shearing threads in any shearing plane, that really will be 100% guaranteed. So anyway, you pair this equation. Really, you could write this out as two: one a shear strength equation and one a tensile strength equation, and then the value of strength is from this table. Table 717 is great. It gives you the gross area of the bolt. You'll notice the root area is smaller. We want to stick with gross area because the code takes into account the reduction in area based on that reduction. So it takes that into account for us, which is kind of nice. Okay, so let's talk about bearing strength. So what we just looked at is the shear strength as though the bolt is getting sheared completely through. The other thing we need to consider is what happens when the bolt impinges on the plate. And if the plate is too thin, then we get different failures here where you can see the bolt has pushed in substantially into the material. So here is a bolt that has a small edge distance. Here it has a moderate edge distance, and here it has quite a large end distance, or so end here as well. So you can see some yielding here, but you can also see some deformation there. All right, these failure modes are handled by these two equations. And there's actually two sets of those, one for deformation considered, and then there's another where it's not considered and these factors are slightly higher. It's better to use the deformation considered because it reduces the joint yielding, and the reality is this tends to work pretty easily with moderate thicknesses of plate, so it's not that hard to make work. Okay, so in here we're going to take the minimum of these two equations. Bearing is this first equation, so it's a function of the bolt diameter, the plate thickness, and the ultimate plate strength. Tear out would be this failure mode. So bearing is what we just talked about. Tear out would be that. It's a function of the length to the end of the bolt. So this from the edge of the hole to the edge of the plate, thickness times the ultimate strength. Phi factor is 0.75. Again, you take the minimum of those two, hit it with your factor, and move on from there. And then I've got a note here, you get 25% greater strength if you don't consider deformation, and we talked about that. All right, slip critical bolt strength, just briefly, coefficient of friction. So that'll either be 0.3 or 0.5. 0.3 is easy to achieve. 0.5 is much harder. You have to blast clean it or use, well, and use a paint that has a coefficient of friction that's class B. So if you spec slip critical bolts and you spec class B, it tends to be more arduous for the contractor, which is fine. All right, so coefficient of friction, this ratio between what you specified and what actually got installed. H of F if you have shims. T sub B is the bolt tension, and then N sub S would be the number of slip planes. So the more you have two slip planes, you get double the strength, which makes sense. Make sure when you're counting slip planes that they're legitimate and you're not taking advantage of things that don't actually transfer force. All right, that T sub U, is it T sub U or T sub B? T sub B is given here, so this would be your minimum bolt pretension. So for a 3/4 inch bolt, 28,000 pounds of force. That's pretty serious. All right, some tables from AISC, which are fantastically helpful. Bolt dimensions, entering in clearance and tightening clearances. So how close can you put the bolts together? Very valuable. Different capacities. So here's a shear strength. So if I have a group A bolt with the threads included, single shear, so the S here, and I have a 7/8 bolt, I have 24 kips of shearing capacity. Similarly for tension, let's say I have a group B bolt, That's 3/4 inch. I have 37 kips of tension capacity. These bolt bearing tables are great. Notice that they're kips per inch of thickness. So any value you have here, we need to multiply by the thickness of material. So if I have an 1.25 inch bolt, which is quite big, with a 2-inch edge distance and 60 KSI, 65 KSI material, I have 77 kips of bearing capacity per inch. So if I have 3/4 inch plate, I could multiply that value by 3/4 and have my strength. The next table is bolt bearing based on tear out, so I need to use the minimum of these two tables. And some of the drivers are bolt spacing and material strength. All right, slip critical capacities. Similar to the previous tables we looked at, you only get shear capacities for slip critical because that's the point. Prying, so this is important. If we have a load applied and the plate, there's like a bending mechanism somehow in the system, which happens all the time in connections, it actually puts a moment on the bolt and causes additional stress. The easiest way to handle this is to size your plate based on the T-min, so it's the minimum thickness where prying doesn't have to be considered. So it's a function of the bolt tension, B prime and P, which are geometry factors, the strength, and a safety factor of 0.9. I start here. If I can't get that to work, you can dive into the equations for prying, which are more complex, but they do give you a slight advantage where you can show things work in prying that this equation doesn't show. All right, some geometric information. So I've provided you this PDF, and let me pull it up in a, I guess this will work. So if I have this joint here, sometimes it's hard to remember or know where all these dimensions come from. And so if you come here, let's say I've got this 1.25 inch edge distance, I can come over here and say it comes from this edge distance requirement. P is standard practice. What does the shop do? And then C is going to come from the connection tables. So I put this together as a way to help you kind of understand for every dimension in a connection where the data come from to design that and lay it out properly. Okay, and I think with that, that's it. I have provided this PDF in a full-blown, not just part of the thing, so it's a little easier to read. All right, good luck with your quiz. Let's talk more in class, and we will end up with greater understanding of bolt design pretty soon.